All right. Welcome back. I thought it would be nice for me to create a little video on some of the concepts from chapter 12. Chapter 12 actually has a lot jammed into it. And so this might be a little bit longer video than usual. But I wanted to go over the concepts from chapter 12, which is focused on electrostatics, electrostatic phenomena. This chapter focuses on charges, the electrostatic force. It focuses on electric fields and electric potential energy and electric potential, two different things, electric potential energy and electric potential, which is also known as a voltage. Okay. So kind of a lot jammed in here. And I'm going to pause. Okay, so I may go between video, writing on my tablet, and the PowerPoint slides, okay, because I already have the PowerPoint slides set up for this chapter, so I'm going to kind of probably be switching between all three of those things throughout this chapter. And I might also show some simulations as well. So here's a common experience that some of you may have had before. Be playing outside, okay. I'm going to brush my hair. And I'm going to brush it. It's kind of a humid day, so you may not see the effects. Well, no, I'm getting it. All right, everybody see my flyaway hair? This is the result of electrostatic phenomena. Okay, and notice when I bring the comb near my hair, the brush attracts my hair. What is actually going on here? Why do the hairs fly away from each other, and why are the hairs attracted back to the brush? What's actually happening here is a transfer of charge. Okay. You're probably all familiar with the makeup of an atom. An atom has a nucleus, which includes the protons and the neutrons in the nucleus of the atom. That's where all of the mass of the atom is really located. And then you have these electrons within an electron cloud surrounding that nucleus. And it's known that when things rub up against each other, so for example, my brush running through my hair, okay, electrons can be transferred from one, thing to the other thing, okay? It's the electrons that are transferred. Okay? The nucleus of the atom is kind of stuck in place. It's not free to move around, but the electrons in that electron cloud are often free to move. Okay, so the electrons, the negatively charged electrons in the atom, are what actually transfers between objects. So between my hair and the brush. Now, I don't really know whether it's the brush transferring electrons to my hair or my hair transferring electrons to the brush. Okay. It depends upon the properties of the material, how that goes. Okay, but there is a transfer of charge, and it's a transfer of electrons, which is negative charge. So let's just suppose it's my hair that's losing the electrons and the brush that's gaining the electrons. So if my hair loses electrons, so I'm basically brushing some electrons off of my hair and they're ending up on the brush, right? If my hair loses some electrons, it has a net positive charge, right? Because it has lost negative charge and you get an overall positive charge on my hair, right? And if the brush is transferring electrons from my hair to the brush picks up extra electrons, and therefore the brush has a net negative charge because it has an excess of electrons. So my hair has a deficit of electrons, so it's positively charged, and the brush has an excess of electrons, it is negatively charged. So all the little hairs here, all the strands of hair, have an overall positive charge. And what do we know about positive charges? Like charge repels each other. So if I try to put two protons near each other, they're going to repel. Okay? If I try to put two electrons near each other, they're going to repel. So if all the strands of my hair have an overall positive charge on them, they're going to be repelling away from each other. That's why we get to fly away. But the brush has negative charge on it. Okay, my hair is positively charged. So what we now see is I'll try to do it one more time. My hair is going to hate me. But we now see that there's an attraction between my hair and the brush. Okay, so what this is showing is that like charges repel and opposite charges attract one another. So conceptually, that's kind of the idea about electrons and the motion of electrons. And you can see that there was a force. There was an attractive force between my hair and the brush. Okay, so we're going to be able to quantify that a little bit in this chapter as well. But conceptually, I just wanted to help you understand, what's actually happening here. There's a transfer of charge, and in fact, it's a transfer of electrons. And if one object has a deficit of electrons and one object has an excess amount of electrons, they're going to attract. So that's kind of, let me see, the idea behind what's going on there. Let's talk about different types of materials and whether they are conductors or insulators. So let me bring up my PowerPoint. Okay, so actually, yes, I'm gonna share my screen and bring up my PowerPoint. So when we talk about electricity, we often hear the terms conductors and insulators, right? What do those terms mean in physics? Different materials behave differently in the presence of electrostatic forces. So if I have a conductor, charge can easily flow through conductors. Most metals are really good conductors: copper, silver, iron, and gold. Even our bodies are good conductors of electricity. So if I place some excess charge onto a conductor, it's going to flow through that conductor very easily. And the excess charge, or those electrons that I place on a conductor, always want to move to an area where they can be as far apart as possible. So if I have a sphere, okay, and let's suppose it's a metal sphere, and let's suppose I transfer some charge to this. So I put some electrons on here. I put some extra electrons on, because originally the sphere is neutral. I have the same number of electrons and protons, so it's electrically neutral. It has no overall net charge. If I put some extra electrons on there, they can flow throughout this conductor. A conductor allows the charge to flow easily. And so let's suppose I put, 4 electrons on here. I'm just I'm just saying, if I have 4 extra electrons placed on this sphere, okay, they're going to repel each other, right? Because electrons repel each other. They're the same charge. They're all negative, so they're going to repel away from each other, and they're going to get as far apart as they can. So there's going to be an electron here, an electron here, here, and here. They're going to spread apart where they can be as far apart as possible. So they're going to spread to the surface of the sphere, and they're going to spread as far apart as they can. They're going to be spread evenly across the surface of the sphere because the sphere is a conductor. On the other hand, insulators are materials that do not allow charge to flow very easily. Okay? Things like plastic, glass, and ceramics, wood. Okay? So if I have an insulating sphere, so let's suppose I have a sphere made out of an insulator. Let's say it's plastic. It's electrically neutral, has the same number of protons and electrons on it, so it's electrically neutral at first. And then let's suppose I place 4 extra electrons on it. Wherever I place those 4 electrons on this insulator, boom, 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 they're stuck there. Okay, if it's a perfect insulator, they will be stuck there and they won't move at all. Okay. So that's kind of the difference between what we mean by conductors and insulators. Both of them can be charged, okay, but it's about how they allow the charge to flow that's different. So here's a question for you. So I have some bits of paper here. I'm going to put them on my little tab. They are electrically neutral. Okay, they have no net charge on them, right? It's basically same number of protons and same number of electrons in each of these pieces of paper. Okay, and the paper is an insulator. Okay, can this piece of paper be attracted to something that is charged? That's the question. Okay, let's see. So if I brush my hair, again, by brushing my hair, I'm basically charging up this brush, right? I'm giving this brush some excess electrons, or vice versa, but I'm just, for our purposes, let's just suppose the brush picks up some excess electrons from my hair. Did you see the attraction? The bits of paper were attracted to the brush. Was everybody able to see that? I don't know if I did it. I'll do it one more time. Sorry. See that? They're being attracted to the brush. Now, why is that happening? The paper itself was an insulator and it was electrically neutral. Why is it that the insulator was attracted to the object that was charged? Well, it's because of what we call polarization. So let me share my screen again. If this piece here is the brush, for example, okay, and let's suppose this was the bits of paper. In the insulator, the electrons are not free to move in the material, so they're kind of stuck. If each one of these little circles is an atom, right, the electrons cannot leave the atom in an insulator. They're stuck, right? They're kind of almost frozen in place. But within each atom or molecule, the charges can move a little bit. So if I bring the brush, which let's just say was positively charged, nearby to the paper that's neutral, okay, what it can do is polarize, what we call polarize the material, okay, the paper. The little electron in that atom wants to spend more time over here, which is closer to the brush, because remember, the negative electron is attracted to the positive charge in the brush. And that happens to all the atoms in the bits of paper. And we have, if you look over here on this side of the piece of paper, we have an overall negative charge. All of the charges over here kind of build up to have a negative charge, and all the atoms over here kind of build up to have a net overall positive charge. The negative charge on this side of the paper is attracted to the brush, and it's also closer to the brush. So there's going to be a larger force here. So we can see that like opposite charges attract each other, and it also depends upon the distance between the charges as well. So a smaller distance means there's going to be a larger amount of attraction here. Okay. So even if an object is an insulator, it can still be attracted to a charged object. It's kind of like when you rub a balloon on your head and you stick it to the ceiling and it sticks. Same idea. Now, if this had been a conductor, right? So if I had brought the brush near, say, like an aluminum ball or something like that. So if it had been a conductor and I brought the brush nearby, brush is positively charged. The conductor allows the electrons to flow freely through it, okay? It can leave the atom and kind of float around. There's like a sea of electrons in the conductor. So what we would see with the conductor is that there would actually be a buildup of negative charge on one side due to all the electrons kind of piling up over here, being attracted to this positively charged brush. That means that there is a deficit of electrons on this side of the conductor, and it's positively charged over here. The same effect occurs that we saw with the paper. There's an electrostatic force, except that it's because the only difference here is that the conductor, the electrons actually can leave the atom and move around freely. Okay, with the insulator, it's still stuck inside the atom, but it becomes what we say polarized. Okay, one side of the atom becomes negatively charged and the other side of the atom is positively charged. And that creates an overall effect. So that's kind of the idea behind the concepts of electric charge. If I actually want to now quantify this, what is the size of the force? Like mathematically, what is the size of the force? There's a force, right? There was a force between the bits of the paper and my brush. There was a force between the balloon and the ceiling. How can I actually quantify that force? Okay. Well, there was a scientist who discovered the relationship between the electrostatic force, the charges that are involved, and the distance. Remember, we said that the distance also plays a role. That scientist's name was Coulomb, and he discovered that the electrostatic force, so I'm going to call this E for electrostatic force, is equal to K, I'll define K in a second, Q1, Q2 over R squared. F is the electrostatic force. Okay. And that force we saw can be attractive if you have two oppositely charged objects. That can be an attractive force, or it can be a repulsive force if you have two of the same sign of charge, like two protons or two electrons. Q1 is the charge on particle 1. I'll just call it object 1. And Q2 is the charge on object 2. So Q1 and Q2 is the size of the charge on each object, and charge, the units for charge, is called a Coulomb. After the scientists, you kind of discover this relationship. We can denote that with a capital C for Coulomb. And so for reference, if you're wondering what a Coulomb is, okay, sorry, one proton the charge of one proton is 1.6 times 10 to the negative 19th coulombs. Okay. And it's positive because it's a proton, and we would denote that with positive charge. Another way to think about this is that 1 coulomb of charge is made up of the charge of 6.25 times 10 to the 18th protons. So if I held 6.25 times 10 to the 18th protons in my hand, I would be holding 1 coulomb of charge. Okay. We don't normally see charge at that level, okay? That's a lot of charge. Usually we see something like nanocoulombs or microcoulombs. And by the way, if you're given like the charge is like 10 nanocoulombs and you need to convert that into regular coulombs, you just write it, multiply it by times 10 to the negative 9th. So this would be equal to 10 times 10 to the negative 9th coulombs. That's how you go from nanocoulombs to coulombs. If you had 10 microcoulombs, if you wanted to write that in terms of regular coulombs, it's going to be 10 times 10 to the negative 6th. Micro is 10 to the negative 6th coulombs. And the charge on one proton is 1.6 times 10 to the 19th coulombs. The charge on one electron is the same magnitude, just opposite signs. So the electron charge is negative 1.6 times 10 to the negative 19th coulomb. Okay, that's how we differentiate between proton and electron having different signs. And R, lastly, what is R here? R is equal to the distance between the two objects that are charged. So as the distance between the two objects goes up, the electrostatic force between them goes down. So that's how we can actually quantify. Oh, by the way, and K. What is K? K is a proportionality constant. Okay. So if I plot the force as a function of the charge and the distance between them, this little k just is like the slope of that line. Okay, it's just a proportionality constant, and we call it the electric constant. Let me make sure I write it down properly. Oh, sorry, it's Coulomb's constant, and the value of it, it's just a constant, and the value of it is, and the units that we will use is 9 times 10 to the 9th Newton meters squared per Coulomb squared. Okay. So if I just, if I plotted the force versus the charge and, or the force versus the distance between them, I could calculate the slope of that line, and the slope of that line would be equal to K Coulomb's constant. Okay. It just tells us the proportionality between all these. And so I encourage you to go through the example box 12.2 to see exactly how to apply and plug in the numbers for finding the electrostatic force between two charged objects. Let me see, what else do I want to, okay. If you have two charges that are opposite sign, okay, you don't actually have to put the sign of the charges in. So if you have something that was like 10 coulombs and then the other charge Q2 was negative 10 coulombs, you know that that's going to be an attractive force. The distance between them is R. You can solve for the electrostatic force, just the size, just solve for the size of it, okay? That meaning that you don't have to plug in the sign of the charge here. You could just solve for the magnitude of the force. And if you want to know the direction, you would just write down that it's an attractive force because the charges are oppositely charged. So the force would just point right along the line that connects the two, right? So this would feel an electrostatic force this way, and this would feel an electrostatic force this way. It'd be the same size for each. Okay, this is like an action-reaction force pair. Charge 1 exerts a force on charge 2, and charge 2 exerts a force on charge 1. Same size force, opposite in direction, but it's an attractive force if the two are oppositely charged. If they're the same sign of charge, the distance between them is R, the electrostatic force is going to be repulsive. So this one will point this way, and this one will point this way. Be the same size force again, just opposite directions. Now let me bring up so far we've kind of just been talking about, hey, what if I have just two charges interacting with each other? Okay. But that normally doesn't happen. Normally we have some kind of distribution of charge, okay, and it affects some other charge. So basically what do I mean by distribution of charge? I just mean, what if I have like a plate, like just a metal plate, and I just like plop, let's just suppose I put I remove electrons from it, and I've got a distribution, a bunch of charges on this plate, and they're all spread out evenly on the plate. And let's just suppose these are all positive. I'm just using positive as an example. It could be negative. Like, so all of these charges are distributed across this conducting plate, and they're spread out evenly across the plate. Okay. And like, let's say I put another charge down here. It would take a lot of work for me to do Coulomb's law between each and every single one of these particles one by one, right? And then I have to sum up the net force. It'd be messy. It'd be very, very, very messy. Okay. What would be easier for me to do is determine the electric field due to this distribution of charge up here, and then determine the force on this charge when it's inside that electric field. So what we're going to learn is that if I have a collection of charges that look like that, the electric field is going to be pointing directly down like that, away from that plate. And if I know the electric field at this point in space, the force that this other charge feels is actually equal to the charge itself, let's call it Q, multiplied by the electric field at that point in space. Okay. So instead of doing Coulomb's law this way, this between these two, blah, 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 too much work. If I can figure out what the electric field is at this point in space, I can find the force on it by multiplying it charge times the electric field. Now, electric field is kind of a weird concept. It's hard to wrap your mind around. So what I do is I make an analogy between the gravitational field and the electric field. So let's think about the gravitational field first, near Earth's surface. So if I'm standing near the Earth's surface, we already learned that the gravitational force is equal to the mass of the object, whatever that mass is, multiplied by g at that point in space, where g, we learned, is the acceleration due to gravity. This g here can also be thought of as a force per unit mass, right? If I solve this expression for g, it's force over mass. Okay, so if I place a 1 kilogram mass right here at the surface of the Earth, it's going to feel a force of 9.8 newtons. Okay. Right? G is 9.8 newtons per kilogram. Okay. We learned it is 9.8 meters per second squared, but I can also write that unit as a Newton per kilogram. So for every kilogram, it's going to feel 9.8 newtons of force. That's another way to think about g, the acceleration due to gravity. It's a gravitational field around the Earth. And it's if I'm near the surface of the Earth, it tells me that every kilogram is going to feel 9.8 newtons of force near the surface of the Earth. That's the gravitational force. The gravitational field is not determined by this little mass that I place in the field, right? It's determined by the Earth's mass, which creates the gravitational field, right? Capital M. The mass of the Earth is what creates the gravitational field of the Earth, right? Doesn't depend upon what the mass I put here. Does not depend. I could put a big mass here, I could put a little mass here. The gravitational field is not affected by this little mass out here. It's affected by the mass of the Earth. The mass of the Earth creates the fact that I'm going to feel 9.8 newtons of force for every kilogram when I'm near the surface of the Earth. Okay, so think about the gravitational field, okay, being created by the mass of the Earth. Now let's relate that to the electric field. The electric force, we said, on a particle inside an electric field is equal to the charge on that particle Q times the electric field. And the electric field, if I solve this for electric field, it's a force per unit charge. It's a Newton per Coulomb. Instead of a Newton per kilogram, it's a Newton per unit charge. If I have an electric field that exerts 1 Newton for every Coulomb of charge, 1 Coulomb of charge is going to feel a force of 1 Newton in that electric field. The electric field is not determined by the charge I place in the field, but by the fixed charge which creates the electric field. It's just like the Earth creates the gravitational field. There's a charge here. Let's just call it capital Q. I'll call it big Q, right? This is the thing that's creating the electric field around it. And then if I place another charge in it, I'll call that little q. The force that it will feel is QE, where E is the electric field generated by this charge over here. So if let me see. I'm going to show you a little visualization that might help. So I'm going to put 1 nanocoulomb of charge in here. Okay. These little arrows are showing me the electric field around this positive charge. The electric field is very strong near the positive charge, right? Just like the gravitational field would be strong when I'm near the Earth. And whenever I get further away from the Earth, the gravitational field drops off. Same way with the electric field. The electric field drops off as I get further away from the charge. So you can see the arrows kind of dimming. Now, how do I know the direction of the electric field? Because the electric field is a vector. How do I know the direction? Oh, I don't want that. Okay. The direction of the electric field of this positive charge is the same direction of the force if I put a positive test charge out here. So let's suppose these little yellow dots are I place a positive test charge right here. Okay. The force here is repulsive. So the force is going to point outward, away. That's the direction of the electric field at that point in space. Down here, if I place a positive test charge down here, the electric field points out. The force points out, the electric field points out. So this is what the electric field would look like for a single positive charge. Let's see what happens when I replace that with a negative charge. What do you think is going to happen? the electric field actually switches direction. Because if I put a positive test charge right here, this is now an attractive force. So the force points inward, and the electric field due to this negative charge points inward. You can see, again, it drops off as I get further away from the negative charge, okay, so that it decreases as I get further away. And as I get closer, the electric field gets really, really big because the force on a positive charge would also get really, really big because I'm getting very close. So it looks similar, but it now points the opposite way. What if I put both in here? Let's see what happens. Make a prediction what it's going to look like if I put both a positive charge and a negative charge. This actually is a dipole, what we call a dipole. Di meaning two. I have two poles, so I have a positive side and a negative side. The electric field points away from a positive charge and towards the negative charge. So if I put this sensor right in the middle, if this is a positive charge, it's going to be repelled from this one and attracted towards the negative one. So there's going to be a really big electric field inside. Okay. And then it kind of curves around a little bit. And as I get further away from the electric dipole, the electric field decreases. Okay. So that's how you can kind of visualize what an electric field looks like. So I encourage you to go through the example box 12.3 to reason about the forces and the electric field at a given point in space for a certain charge configuration. The last part of this chapter is focused on electric potential energy and electric potential. So electric potential energy and electric potential. Okay, now this is where it starts to get, I would say this is where it starts to get a little bit more tricky. I'm going to write down an equation and then I'm going to explain what it means in a bit. Okay. I'm going to set up a situation in which I have two plates. So this is a 3D thing. These are conducting plates. And let's suppose on the top conducting plate, we have an overall positive charge on it that's positively charged. It's spread out evenly across this conducting plate. And on the bottom, we have another plate which has negative charge spread out evenly on it. The electric field, I don't know how to change, oh, here we go. The electric field between these two plates, let's just first think about the electric field first. If I was going to visualize or draw what the electric field looks like between these two plates, remember the electric field lines point away from positive charges and towards negative charges. So the electric field lines are going to point like this. And they're going to be like, if all those little arrows like you saw in the simulation I showed, they're all going to be pointing down. I'm just drawing a few lines just to, help us visualize it, but there's an infinite number of lines here. But I hope this kind of helps you visualize what the electric field looks like. It's a vector quantity, so it has a size and a direction. So the electric field here is pointing away from the positive charges straight down towards the negative ones. Now let's think about what happens when I move a charge around in here. Okay. So let's suppose I put a negative, well, no, let's do positive. So let's put a positive charge in here. If I put it up here near the positive plate and I just try to hold it there, right? That takes a lot of energy for me to hold it there. It doesn't want to be near the positive plate. It wants to fly down towards the negative plate, right? So what I would say is that this thing has stored energy when it's up here, right? And that energy, if I released the thing, could be converted into kinetic energy to make it fly down here to reach the bottom plate because it's attracted to it, right? But when I hold it up here, it's like holding it against its will. I'm holding it hostage, right? It doesn't want to be up here. So it has stored energy, potential energy, right? It has electric potential energy. It's like holding a mass at a certain height above the ground, right? It has stored energy. It wants to fall to the ground. It's attracted to the earth. It wants to fall towards the earth, right? So holding it up in the air against its will um, allows it to have stored energy. Okay. So as this thing moves down, right, through this electric field down toward the negative plate, it's going to have a change in its potential energy. We don't always talk about electric potential energy though. And that what we actually talk about a lot more in physics and electricity and magnetism is potential. Okay, so this left-hand side is called electric potential energy. Its units are the same as any other energy. Its units are going to be in terms of joules. What do I have on the right-hand side is this delta V. This means a change in electric potential. It's different than electric potential energy, even though they sound almost exactly the same. Delta V is the change in the electric potential. You might also have heard this term instead as voltage. We will talk more about voltage in the next chapter, which is focused on circuits, but we need to get a conceptual understanding of what voltage is first before we can talk about it in the context of circuits. And Q is the charge, is the charge on the object. So if I solve this for electric potential or voltage, delta V, I've got the change in the potential energy, the electric potential energy per unit charge. So it's a joule over a Coulomb. Okay. So potential, electric potential, or voltage has units of joules per Coulomb. Another another way to say joule per Coulomb is a volt, or V for volt. So that a joule per 1 joule per Coulomb is the same as 1 volt. Okay. So what does this mean? Okay, if you take a look at a battery, for example, okay, just say a regular old AA battery. When you read on the battery, a AA battery says it has 1.5 volts. What that really means is that there is a potential difference across the battery, a change in the potential across this battery of 1.5 volts. So one side of the battery can be considered to be 0 volts, and the other side of the battery can be considered to have 1.5 volts of electric potential. And if I send, for example, if 1 Coulomb of charge goes from 0 volts on one side of the battery to 1.5 volts on the other side, so if I move 1 Coulomb of charge from here over to here, and I push it through 1.5 volts, that means that the electric potential energy of that charge has increased, right? Delta PE is going to be 1 Coulomb of charge, that's Q, times the change in the potential, which is 1.5 volts, or joule per Coulomb. So that means that the charge has gained 1.5 joules of energy, electric potential energy, as it goes from one side of the battery to the other. So that's what we mean by volts. Volts is a more generic way to think about some electricity, because we don't often talk about, okay, 1 Coulomb of charge went through the battery and it gained this much amount of energy, right? Because, there's charge going through the battery all the time. So why do I need to talk about that? I'd rather make it more general and say the battery has 1.5 joules per Coulomb. Okay, the battery provides 1.5 joules per Coulomb for charge that passes through. Because otherwise, when I'm talking about electric potential energy, I have to talk about how much charge passes through, right? And there's so much, once we connect this thing to a circuit, there's so much charge that's like passing through it, it's just more confusing. So we normally just talk about something having a certain amount of voltage. Basically, it's providing potential energy. A battery provides potential energy, okay? And the amount of potential energy depends upon the voltage of the battery. A larger battery is going to provide more potential energy. So that's what I mean by potential and the difference between electric potential energy and electric potential. Electric potential is voltage. And it's a little bit more generic. When I am near a positively charged plate, I'm at high voltage. Because if I place a positive charge here, it has a lot of potential energy. So therefore, it has a high voltage. If I'm near a negatively charged object, it has that you would be at a lower voltage. Because if I place a positive charge here, it doesn't have very much potential energy at all. That's where it wants to be. So its electric potential energy is low. It has low voltage there too. And so what's the relationship between the electric field, the distance between these two plates, for example, and the voltage? Okay. So let's suppose I know what the electric field is between the plates, and let's suppose I know what is the distance between these two plates. Remember, if I do work in lifting up a book, right, against the force of gravity, I do work on that book. The work that I do is equal to the change in the potential energy of the book, right? Same thing happens here. If I push this positive charge around in this electric field, whether I push it towards the positive side or allow it to go down, there's work being done, right? So let's suppose I push this positive charge from the bottom plate down here where it wants to be, like on the ground, for example, up to the top plate where it doesn't want to be. I did work on it, right? I had to do work to push it that way, and that work is equal to the change in its potential energy. The work I did has to be equal to the force multiplied by the distance. Remember, work is equal to FD. And the force that I have to exert here is the force that this feels in the electric field. And if you remember, the force, the electrostatic force in this electric field is equal to QE. So I'm going to replace that with QE over here. Is equal to the change in the potential energy. So I push this thing from the bottom plate to the top plate. I'm doing work on it. It's gaining potential energy. And in this case, the potential energy change is equal to QED. But hey, we said the change in the electric potential energy is also equal to the charge itself multiplied by the voltage across the plates. Right? If I know the voltage on the top plate and the bottom plate, I know the change in the voltage, right? Let's say this is 10 volts up here and this is 0 volts down here. I know the change in the voltage. It'd be 10 volts. So the electric field times the distance between the plates is equal to the voltage across the plates. This works for this will only work for electric field that is uniform like this. Okay. but we won't do we won't deal with this relationship for a situation in which the electric field is not uniform. So don't worry about that. Okay. So if I know the electric field between the plates and I know the distance between the plates, I can determine what is the voltage between the plates. And I can also go the other way too. So you might have a few questions on your homework that deal with something like this. Now that brings me to talking a little bit more about a battery and kind of what it does. So let me bring up my slides again, because I had a nice diagram of a battery. Right. Sorry. So again, a battery, let's suppose simple AA battery. When you look on a AA battery, it says 1.5 volt battery. And you've got the cathode, which corresponds to the positive side of the battery. The anode corresponds to the negative side of the battery. What does a battery actually do? Oh, there's a chemical reaction that happens inside the battery due to this electrolyte. You've heard of battery acid and things like that. There's a chemical reaction that's actually happening inside the battery that causes negative charge to build up on the anode, right here. Don't know why that's being funky. Okay. It forces the negative charge in this electrolyte to float down towards the anode. How it does that, ask your chemistry teacher. But it's just a chemical reaction that's what happened. The negative, and so then because there's a negative buildup on the anode, there's an deficit of electrons over here on the cathode, and it ends up becoming positively charged. The electrolyte prevents negative charge from moving backwards towards the cathode, right? So in a battery, if you have a buildup of negative charge on one side, it's not going to be able to flow back towards the positive. It's not going to be able to flow to where it wants to be. So these negative charges over here on the anode, they have potential energy, right? They're forced into being somewhere where they don't want to be due to this chemical reaction. There's a potential. There is a potential difference across the battery, and there's a potential energy difference. Now, once I connect it to a circuit, so now if I connect the battery to a wire that conducts the electrons, there is now a path for the electrons to flow through. Now they can move towards the positive end of the battery to be where they want to be. There's nothing blocking them anymore. They can go and go back to the positive side. They couldn't do that before, right? They couldn't flow back like this because the electrolyte stopped them. Now, once I connect it to a circuit, the charge can flow. And this process, this process continues on continuously. Okay. And so this potential energy, right? We said, hey, these electrons have potential energy. They're pushed towards the anode. They have potential energy. What happens to that potential energy? Well, it gets used to light up a light bulb, for example. Run your toaster. The energy that it has can be converted into different forms of energy: light energy, heat energy. And when it gets back to the cathode, it starts all over again. right? It gains this chemical reaction occurs. The electron gains potential energy as it gets pushed through the battery, and then as it flows through, that gets converted into other forms of energy. So the battery is almost kind of like a water pump, okay? The water pump pushes the water up against the force of gravity. The water can't flow back through the pump, right? So it sprays out, back into the pool. And that falling water could be used to power things, right? Just like these electrons can be used to power things. So that's the idea behind a battery and what it does, and why do we see a 1.5 volt on a battery? That's what that actually means. If 1 coulomb of charge passes through this battery, it has gained 1.5 joules of energy, potential energy. And that 1.5 joules of potential energy can then be converted into other forms of energy, and then the whole process starts over again. We will get more into circuits in the next chapter, but I just wanted to go over it because we use batteries all the time in our everyday life, and this is exactly what's happening. Well, a very simplified model of what's happening, right? But important stuff. So that's the concepts from chapter 12. Still read through the chapter, work through the examples to help you solidify your understanding of how to actually solve these problems involving electric force, electric field, electric potential energy, and electric potential or voltage. A lot jam-packed in here. Okay, but I hope I helped a little bit with covering it. If you do have questions, let me know. The homework for this chapter won't be due until July 11th. I pushed it back since we have an exam. So, but email me to set up a time if you need to meet to talk about the concepts. I will continue posting these videos as best I can for the rest of the semester. Anyways, email me if you have questions, and I'll talk to you soon. Bye.